Today we'll step through an example of a working neural network. I have an XOR data table right here, and we're going to start training this neural network based on this data. This data table has two inputs, x1 and x2, and two outputs, y1 and y2. Our neural network has two input nodes to match the two inputs, two output nodes to match the two outputs, and also has two hidden nodes. XOR is a function that says, given 2 bits, if exactly one of them is true, the answer should be true. Usually we'll have just one output for an XOR function, 1 meaning true and 0 meaning false. But with one output, the backpropagation math gets a little too easy, and you wouldn't get a good idea of how backpropagation works. So what we've done is encoded the y1 output to mean true, and the y2 output to mean false. So in the first row we have bit 1 set to 0, bit 2 set to 0, the answer is false, so we have y2 coded as 1. In the second row we see that exactly one of the bits is true, so our result should be true, so y1 is coded as 1. Similarly in the third row the result is true. In the last row both bits are set to 1. The XOR function looks for just one bit being set to 1, so the result is false. We are going to take one row of data, run it through our network in the feed-forward direction, get a result, compare it to the expected value, run through the backpropagation phase to train the network, and run the same example in the forward direction again to see that some learning has actually occurred. So we'll present these values, 1 and 0, to our neural network. The input nodes have a very simple job. When they see some data, they simply need to fire and let the next layer hidden nodes know that there's some data available. So x1 will fire, and x2 will fire. They each call receive input on A and B. Since A has received all of its input, it says, I'm ready to calculate my value. It calculates its own value by finding the weighted sum of all of its inputs. So the value of x1 is 1, we'll multiply by the weight 0.7, and we get 0.7. The value of x2 is 0, we multiply that by the weight 0.3, and of course the result is 0. So our weighted sum is 0.7. But that's not all. Remember that we have to run that through the sigmoid activation function to ensure that our resulting value is between 0 and 1. We'll do the math on this the first time. So we received a weighted sum of 0.7. Plug that into our function. And we get approximately 0.67. So we'll put 0.67 in as the value of node A. We'll do a similar process for node B. Again, the value of x1 is 1. The weight this time is 0.1, so we get 0.1. The value of x2 is 0 times 0.9 equals 0. So our weighted sum is 0.1. We look up f of 0.1 and we get 0.52. So the value of b will be 0.52. We're now ready to work on the outputs. So for output y1, we have the value 0.67 times 0.2 is 0.134, and 0.52 times 0.6 is 0.312. So the weighted sum is 0.446. We plug that into the sigmoid function, and we get 0.39. For y2, we'll take 0.67 times 0.5 is 0.335, and 0.52 times 0.8 is 0.416. Our weighted sum is 0.751, and we calculate f of 0.751 and get 0.68. So now we have the output of our first pass through our neural network. Notice that the network actually chose false for this example. False got a score of 0.68 and true got a score of 0.39. We picked the larger one, so we say that the network feels the answer should be false, when in fact it should be true, so we've got a little training to do. When we have our production net running, what we'll do is run these examples, all 4 of them, thousands and thousands of times, until when we run example 3, for instance, we get close to 1 for true and close to 0 for false. So now let's look at the backpropagation phase. We know what answers we wanted. Now we just have to nudge the network in that direction. There's one more parameter we're going to need called the learning rate. And we're going to choose a really high rate so we can actually see these weights move. We'll choose 0.8, but actually when you run a neural network, a more typical learning rate is 0.01 or maybe even 0.005. It's a parameter you can play with and see what kind of results you get. Another bit that we're going to need is the derivative function of the sigmoid function. You can look up the math, but the derivative function for this turns out to be very easy. That's one of the reasons why we choose this function. So the derivative, which we call f prime of x, turns out to be just f of x times 1 minus f of x. And since we already calculated f of x, that's the value for each node, we're actually going to simplify this. We're going to say f prime of x will end up equaling the value at the node times 1 minus the value. And this is the function we're going to use. The delta function will tell us how much we need to move the weights by, and the function is expected value minus value times the sigmoid derivative, which we simplified to value times 1 minus value. Now this is the delta function for an output node. An output node is right next to the expected value. It knows what it wanted to get. It knows what it got. The hidden nodes are going to have a different function because they're farther away from the expected value. But let's go ahead and calculate the delta function for output node y1. The expected value was 1. The actual value it arrived at was 0.39. Again, value is 0.39. And 1 minus 0.39. That's a lot of 0.39s. And the result I got is 0.15, approximately. So we'll note that here and move on to y2. In this case, the expected value was 0. Actual value was 0.68 times the sigmoid derivative equals approximately negative 0.15. And the signs on these are no coincidence. This value needs to move up a little bit, and this value needs to move down a little bit. The hidden nodes are just a little more complicated. They're not really close enough to the expected value and output value to use those to update their weights. So instead, they're going to take the deltas as an indication of how far off their prediction was. Node A contributed a little bit to the output of y1 and a little bit more to the output of y2. So again, we're going to calculate a weighted sum. And this time, instead of looking at values, we're going to look at deltas. So the delta for node A is going to be the weighted sum of the deltas for node y1 and y2 times the sigmoid derivative. So we'll calculate the weighted sums first. From y1, we had a weight of 0.2 times a delta of 0.15. And for y2, we had a weight of 0.5 times a delta of negative 0.15. So we get 0.03 and negative 0.075. And our weighted sum is negative 0.045. Again, we'll take that and multiply it by the sigmoid derivative, this time focused on the value of node A, and we get negative 0.01 approximately. I've shown all the math here for node B. I'm not going to go through it, but you can confirm that the delta for node B should be also approximately negative 0.01. So now we're ready to update the weights. Notice that we had to use these weights in our calculation for nodes A and B, so we couldn't update them yet. We didn't want to update them until we'd used our prior figure to figure out what the accurate delta should be. So here's the formula to figure out the new weight. The new weight of an incoming node should be its current weight plus the product of the value of the incoming node times the delta times the learning rate. So if we're focused on this weight, for instance, 0.2, we'll find the new weight by taking the current weight, 0.2, plus the value of the node that it refers to, 0.67. Remember, we're looking backwards, times the delta of the output node and times the learning rate. And the result we get for this weight is about 0.28. So our weight was 0.2, but we will update it to 0.28. Notice the effect that's going to have. It was 0.2, it was a multiplier, so that's going to have the effect of pushing this number up towards 1. And now we need to calculate the weight for the incoming node B into node Y1. Again, we'll start with a current weight of 0.6. We're going to add the value of the incoming node, which was 0.52. We're looking from Y1, backing up. Remember, this is back propagation. We're backing up to the node that's contributing the value of 0.52. We have a delta in our node of 0.15 and a learning rate of 0.8. And our result is approximately 0.66, which again is pushing this number upwards towards 1. We want Y2 to head towards 0, so we should see these weights go down. For the incoming weight from A, we take the current weight, 0.5, plus the value of A, times the delta. I'll put it in parentheses since it's negative, times the learning rate. And we get a result of about 0.42, which is smaller than our previous weight of 0.5, so we're making progress. We'll speed through the calculation for this last weight. It was 0.8. We take 0.8 plus the product of the value of B times the delta of Y2 times the learning rate, and we get a new weight of 0.74, which is in the right direction. The process for calculating the weights going from the input layer into the hidden layer is exactly the same. I'll go through the first one here. We have a current weight from X1 to A of 0.7 plus the value from X1 of 1 times the delta, negative 0.01, times the learning rate, 0.8. And we see that's approximately 0.69. I'm going to let you verify the rest of the values. Notice that these two didn't move at all because node X2 had a value of 0, so it didn't actually contribute anything to these values. So now that we've calculated new weights, we can get rid of all these deltas, and we can also remove the previous values from the hidden and the output nodes. I'm just going to save our previous results up here so we can compare them as we go through the network again. So now we're going to present the exact same example to the network. Generally, we wouldn't do this. We'd present maybe in random order or sequential order. We'd present all the examples over and over again. I just want to show you that our network learned a little bit about this one example. So if we multiply 1 times 0.69 and 0 times 0.3 and add the results, we get 0.69. F of 0.69 equals approximately 0.67. Here for B, we'll multiply 1 times 0.09 plus 0 times 0.9 is 0.09. And F of 0.09 is 0.52. We multiply 0.67 times 0.28 and 0.52 times 0.66. We get a sum of 0.53, and F of 0.53 is 0.63. And finally, we take 0.67 times 0.42 and 0.52 times 0.74. We get 0.67, and F of 0.67 is approximately 0.66. So we can see we've made a little progress. The first time we ran this example through the network, we got a result of 0.39 for true, and the second time we got a result of 0.63. So that's closer to our expected value of 1. On the false side, we didn't move as much, but we did move in the right direction. Originally, we got 0.68. After the back propagation phase and then going through feed forward again, we get 0.66, which is closer to 0. So just a couple notes on what we did that may be a little bit simplified. One thing we did is we chose the same example twice. Generally, we wouldn't do that. What's happening is we're going to train hard on this example if we keep doing that, and the other examples aren't going to get any exercise at all. So our neural network will correctly respond to example 3, but probably will have incorrect responses to the other 3. Another thing we did was we forced a very high learning rate. That caused our numbers to move pretty fast, But again, it's going to favor whatever the last example you presented was. Generally, we'll use a learning rate of 0.01 or 0.005 or something small like that. We only use decimal precision out to the hundredths place. In fact, we're going to use decimal precision to many, many, many digits when we actually run this in production. And you'll see that each time through the neural network, if you watch the numbers change, they only change a very little amount, maybe out to the 10,000ths or 100,000ths place. But we train this many thousands of times, and slowly the network inches toward better results. We also updated our weights after presenting just one sample. That's actually okay, but production neural networks often will run all the examples, called an epoch, before updating the weights. It just makes the math a little more complicated. And that's it. I hope this gives you a little more insight about how our neural network works, and hopefully gives you a little help for assignment number 6.